Hello, welcome to Bedroom Builds at the From Python to Rust series, episode 10, Smart Pointers, coming from the previous episode where we spoke about debugging. So smart pointers in Rust, you can actually argue that we already used them because the whole borrow checker mechanism basically makes everything that you referenced as a mutable or immutable reference cleaned up at the end of the scope. And therefore the compiler basically is being the smart pointer for you. If your code, however, needs to help the compiler understand what is going on without going back to using unsafe code like you would in directly memory managed languages, you will have to use smart pointer structs that are provided to you by the standard library of Rust. All of this smart pointer stuff that we will discuss today will be automatically or automagically done for you by Python or other garbage collected languages, because there the garbage collector will clean up after you and will already have internally reference count and all the other stuff. For C++ programmers, you might know the unique pointer. This is the same thing that Rust provides to you with a box. A box we have already used in error handling, for example. There we needed it to use trait types to give back everything that implements the error trait. We had to use the box din trait, if you remember. And another thing where this is useful is if the size of your object is not known at compile time. Right now the Rust compiler would have to have this wrapped in a box to understand the size, because it knows the size of a box. Therefore, if you create this object, then every time on the heap wrapped in the box, it will be happy. This will be useful for recursive structures, for example. Then a shared pointer from C++. The equivalent would be something that is called RC, so reference counted pointer in Rust. That thing basically does the reference count, so how often it is referenced. And if the reference count goes to 0, the system knows, oh, this is no longer used. I can free this without an issue. And the last one is the weak pointer, in Rust simply called weak. This is a version of the reference counted, the RC pointer, that is not owning the reference to the managed allocation. Therefore, weak not being the owner of the reference. And if you want to know more about all of these smart pointers, tricks, and necessities, I strongly suggest you read the article Learn Rust with entirely too many linked lists, as in there it will go into detail as what is a good practice and the bad practices using that, and why you should probably resort to other data structures and not linked lists in most of the cases anyways. All right, let's hop over to our first code example. So in here, we are going through the box again. So in the first useful line that is not import, we define our result type. And the result type is of type result for the type T, and we return the box din error for any errors that can come up. We then use this here in our main function, and this is just to remind you that this is a good use of a box in practice. Another one is, for example, in a list struct that you've created, you might want to have this as a linked list, and there you can go. The next element of your list will be optional, so you might have a next element or not, and you will use a list again inside. So list is having a next element of type list. Now, if the compiler would look at this, it would try to figure out the size on the stack for this struct, meaning next has to have a size. Okay, with option it can deal, fine. If we didn't have the box and we just had the list in here, it would not be able to figure out the size, because now it would look at the definition of list again, see that next, see list, wants to figure out the size of it, and this will be an infinite loop, right? The only thing where we know the size of is our value, which is an i32. And in order to give it a sized information, to give the compiler a sized information, we use option to be optional. Box then gives it a heap allocated memory. The size of this is known, and in box you can put any type. So in our case, it's self-referencing list again, and it works out. Below, we have a minimal example of a box that uses an integer. But here it's not guaranteed that this will actually be something that is heap allocated. The compiler might figure out, oh, this is an integer. I can do that right away on the stack, and it may be optimized away. I don't think that Rust does this right now, but if you're really using this, don't be 100% certain that it will stay this way for primitive types. Below we have an output that shows us what's going on with our box, and here we instantiate our list that has at this instance no next node, but here we attach a next node, and in order to create this we also have to use box new again and our list element, and then we can print the list's value. And the first minimal use of a reference counted is then coming at the bottom. So we have the A dereferenced. So this is our box from up here. And if we dereference a box, we actually get the value inside. So this star A actually gives us 5. Therefore, we can create a new reference counted pointer that we call B that will hold a 5 behind its reference count. And then we have two options to make the reference count increase by cloning. And if we use the static method provided by the reference count struct, so rc clone, and then a borrow of our reference count b, this will be a very cheap operation, as you can see here in the comment. This will only increase the reference count, and now we have another one called _c, because we don't use it anymore. I used it with an underscore. And below I print the current ref count for B to see if this really was increased. And below the second way of doing it, we can actually use a method that is attached to B called the clone. And the difference is you can now here explicitly say, all right, I'm only increasing the reference count. And here, this can actually, if it is a more complicated object than just an integer, be deep copying the data inside your reference counted pointer. And this can be an expensive operation. So you might not want to do this, or you explicitly want to copy, then you should use this clone. If you really only want to increase the reference, because that's all you need in your code, you should resort to using that, as this is way more explicit. And here it can be only a reference count increase, but could also become or is already a deep copy, and that's expensive. We check again the reference count, and in order to make a compiler happy, we return an empty unit, because this is our result type up here. Let's run this code. Rust compile our smart pointers.rs and run smart pointers. So the first output that we have is 5 and 5. It's twice the same, even though we use different ways of printing. So here we have a debug output. Here we have only a value. First we debug the box, but a box is only a thin wrapper to give you the data that is on the heap. So it will actually just automatically present the data it holds for you. Therefore we just get the 5 and no further info. And if we dereference it, we actually get the 5 out of our box. And this is why this normal print statement formatting command works. Then below, we only have list value 1 printed out, and it's true. So the first element of list is L value. The point of this was just to show you a second way of where a box could come in handy. So if you have a recursive struct in your code, you might want to use a box for that. And below we come to our reference counting example. So the first one already has a reference count of 2, and it makes sense because here we created our first reference to A, so this will be 1. Then we clone it, and if we clone B to our here called _C variable, then B has a reference count of 2 already. And then if we do clone again, this time with the method of B, it will be increased again by 1. And both of them are still pointing to the 5, so the first variable output on the left here will be our 5. I've prepared a more elaborate example of showing how the reference counting works automatically for you in Python and how we can use that in Rust. So let me open this code. This means we have to get out of our Rust shell, open the RCPy, hop over here, open the RCRS. All right, so on the left, what do we have? We create a string that is called RC examples, as we do on the right in Rust. That's the same. Then we have this system getRefCount method that allows us to give us the information of what Python in this case, of course, has as a current reference count for our RC examples string. Then we create a scope. In Python, I have to use nested functions. In Rust, I can just use the curly braces to create scopes. And in here, in our scope, we would then just assign RCA to our examples variable, and we can then get the reference count for that one. And in our subscope, again, we do the same trick. We assign it to another variable, do some stuff with the variable. In our case, it's really only getting the reference count. We just call the scopes as well, so that our Python interpreter actually does the things we want. And every time we get our reference count to see what's happening to it when we then start leaving scopes. On the right side, we also do that, but here we have to explicitly tell the compiler that we want to have a new reference counted pointer. And we create one by this line. Once we have it, we can use the static method strongCount to figure out what is our reference count, as we already used in the first code. Then here we use the static method to clone it to get another increased reference count into our RCB. Here we can then check the reference counts of A and B. Then later we can see here in the comment it explains, we can check the equality of the inner values of the RCs. So this does not compare the pointers, this compares the actual values inside. And you can also easily use the actual reference counted pointer as if it was the value. So you can directly call len and it will call length on the string and not on the reference counted pointer. And the same is then true also for just printing the value. You can use the normal value formatter to get what you have inside your reference counted pointer. So the last strong count, as we have on the left, and once it drops out of scope, this should become 0 and be cleaned up just fine. Let's check out the Python code first. So if we run Python 3 on rc.py, we actually get an output. I've tried to research why right after we created the string, the reference count is already 4. I know from documentation that getRefCount increases the reference count by 1, because in order to get the ref count, you are actually passing an reference counted pointer to this function. Therefore, it will be +1. This means that the actual count after this method was run is actually 3, but why is it 3 from the start? I have not found out yet. It should be 1, but it's not. But anyways, it is consistent increasing afterwards, because what we do is we create our RCA, therefore an increased reference count, and it's true. It goes from R4 to 5. Once we enter the next subscope, we actually have RCB assigned, this means that should be higher. And if we do check it, it is 6 for both. And it makes sense because both A and B actually reference our examples. So we went from 4 to 5 to 6. And in both cases, it is, of course, 6. If we now, just to be sure, check what is the reference count of our examples variable, it is 6. So it's true, all of these three are pointing to the same thing. Now, the stuff goes out of scope when the subscope function is run, right? So right after here, in this print statement, RCB will have a lower reference count, and it's true. We are going down to 5, and then we leave the scope of our inner scope function, and this is then this line, and we are back to 4, which is what we started with. So Python does this for you. You don't have to think much. You don't have to use specific smart pointer structs to do any of this. You just write your code as if you are talking, basically, and everything is fine. In Rust, we have to tell the compiler what we want, but it works just as fine. So we compile our RC example, we run it, and here we can see that if we have the reference count at the beginning, it will be 1 because we already created a reference count here to our string. So the first one has a count of 1. Then for the B, it gets increased by 1. But this also means that for A, it will also be 2 because both of them point to our actual examples string. Then we get those two are equal. Well, yes, the values are equal. They point to the same string. And the length of the string is 11. So that works fairly easily. Once you have created your RCs or other smart pointers, you can just use them as if you were using the value directly. As you can see, this prints it also just fine. Below, we get the reference count of 1 again. Why is that? Well, we entered a new scope to create RCA, then another scope to create RCB, but we are leaving this scope, so we are back to the reference count of 1 because this is no longer referenced twice because it already went out of scope and the compiler already made sure for us that it gets decreased by 1. In order to show you how you can use the weak pointer, there's one more code example that I have. Let's hop over to this one. This needs some more explanation because what we are creating here is fairly complex stuff, as you can see already by the code being very long. I have prepared a graphical representation of what we are building. We will have a pseudo implementation of a binary tree. So we start with the root node, but every node has a parent, has potentially a right node and a left node. And if the parent node is assigned, so in our case we created something called node 2 that does not have left or right nodes. The root node has no right node, has a left node though. This left node's parent, of course, is the root node. And they don't have any left or right nodes. So this is the structure that we will be using in our code in both cases, in Python and in Rust. So let's hop over. In Python, I've created this node class that gets initialized with no parent, no left, no right node, and the value that you have given at the constructor. Here we have the representation implemented in order to print this in a nice fashion. And we print only the value of the parent in order to avoid having too much output that confuses us, because if I printed the parent, it would go in here again and recursively write out all the information of the node, which will be hard to read in the output. However, we print out the full left node, the full right node if exists, and of course the value just using v here. The code itself is then fairly easy to use. We create a root node with the value 0. Then we create a node that has the value 1. After that, we assign the parent of our node to be root, which we saw before in our graphical example. Then we have the left node of root is node. So we assign that one. Then we create our node 2 with the value 2. And this actually is the parent of root. Therefore, actually, root is no longer root if you want. Below, we print the whole node root. To avoid running into a too deep recursion, we have to reset our printed set of the node namespace. And because this is the way we check if this was already written out or not. And then we get the root's left node's parent's value, which, if you remember from the graphics output, will actually be root's value because the parent of our left node is root. So root's left node is node, but the node's parent is root, so therefore it should print 0. And reset again for our printing. And below we just get our IDs to see that those are equivalent. So the root's parent is node 2, therefore the ID of node 2 and the parent have to be the same. And then the next code that we have in our main is we tell the garbage collector, ooh, we can actually get rid of node 2, I don't need it anymore. Then we also assign the parent of root to be none again, and then we can see what happens to our root parent representation. Let's run this and see what happens. So we jump into Python 3, bin tree, and we get some confusing output. So what's happening is we get node is the output that we have here in our formatting string. The parent of our root node is 2, which makes sense because node 2 is the parent of root, right? Then on the left side we have a node again that is having a parent with the value of 0, which makes sense because the root node has the value of 0 and the parent of our left node is, well, itself root, right? Left node we have not assigned to anything of our node and the right node as well. So node with the value 1 has no right and left nodes but a parent, and the parent is the root node with the value 0. And since all of this is nested, so from this node the right path is not going to a node and the value of this root node is 0. So that's the output of just this line. If we now look at the parent's left value, it is 0, and that makes a lot of sense. As we said before, the parent of the left node is root itself and the root's value is 0. The IDs indeed match between those two, and it makes sense because, well, all we did, we assigned the parent to be node 2, so of course they are the same. Now here we delete node 2, set the parent to none, and then this of course tells us that the parent is none. We will get into more detail of this a bit later when we come to our Rust example. Now let's hop over to the Rust code again. Okay, let's compare the Rust code to what we've done in Python. All right, so we have to use refcell in order for this to be easy to use, basically. So refcell, as our comment here says, is basically a runtime borrow checker if you want. So what this does is it gives you the ability to allow for interior mutability, meaning that within your struct node, even though you might assign it to not be mutable, you can actually borrow out of a refcell and still mutate the elements. That's very practical, for example, for mock objects that you want to use in testing, where the code only allows for non-mutable instances, but you will still want to trace, for example, some side effects in order to prove that your test has success. You can also use this to provide APIs that hide the internals of your structs, so you don't allow mutable structs, but you can still internally modify your code. The downside of using the ref cell, of course, is since this is done at runtime and not at compile time, the compiler cannot optimize as well as it can with the normal references, with the normal borrow checker. The downside of using ref cells is they are run at runtime, so the compiler cannot guarantee at compile time that the borrowing and mutability is used fine already in your code when creating the code. Therefore, it can also not optimize as well. And you might run into panics while running your code because there might be two mutable borrows happening at the same time. Then we import the debug to have our node printable, and we get our reference counted and our weak pointer. Now, in order to construct the node as we did on the left in Python, we have the parent, and this is an optional one, right? So here it can be none, and in order to allow this in Rust, we have to use option. Inside option, we use weak for the parent, because the parent might go away, but this is not a problem for our node. Then we use refcell to be able to mutate that. Then our type node, and since this is generic programming, we used the type T for our node. This is why we have this long line of definitions. Then for our left and right node, we use strong references. Therefore, we have an option of a reference counted one. That is also refcelled in order to mutate it, and is of type node of type T. Now value is of type T. This means we can use this generically. We implement a constructor to have the ease of use and similar code like we have here, where we just use a node 0 and everything is done for us in a meaningful way. And I created the print parent method to not have to redundantly write all this pattern matching deconstruction to get to the parents if they exist, and also check if the weak pointer actually has some meaningful value behind it. So what this does is it first checks if there is some value in your parent. So if the option actually has a sum, we get into this if block. If not, we can actually directly print, well, this is none and there is no parent. If there is, we can try to upgrade the weak pointer back to a reference counted one. If that is the case, we will get some reference counted pointer back. This then means we can borrow out of the ref cell and get the value inside of our node, and therefore print the parent's value. And if this is not the case, so we cannot upgrade, there will be a non-returned. We will here be more explicit and don't just print the none. We will actually tell you that the parent no longer exists. So the weak pointer will still be there, but it does not have a meaningful allocated value behind it anymore. Let's keep going further down in the code. Here we map to the main code that we have in Python on the left. In order to create, however, this node, we have to do some more stuff, because we have to create the reference counted pointer that holds a ref cell that holds our node with the value 0. In order to create the node with the value 1, we do the same. Now, in order to assign the parent, we use our node, then ref cell borrow mute. So we mutably borrow into our nodes. Then we get the parent. We can assign sum, and we have a weak reference, if you remember, in here. So in order to get the weak reference, the idiomatic way is to downgrade an RC, and we have the reference counted pointer to root. So we downgrade this one with the static method to a weak reference. And this way we can assign some weak reference to our parent. Then we create our node 2 with the value 2. Here we then can mutably borrow, set the parent again to the weak pointer, and the left node of our root will become the actual node. So this matches exactly the code that we have on the left here in Python. In order to print like here on the left side in Python, we will use the debug formatter, and then we immutably borrow from the ref cell our root node, dereference it, and this then gets printed here. If we want to check if we have a left node in our root node, what we do is we use a reference to root, immutably borrow the node from it, from the ref cell that is inside our root, get the left. This can be none, but here we only match it if it is some. If it is, we then immutably borrow the node inside the left and call the print parent method on it. This is similar to what we're doing here. And the same is then happening down here twice again to see what happens when we drop from memory the node number 2. Now let's run this example. So we have run our code, and the root printing gives us our node. This has a parent that is a weak pointer. It has a left. Here we have the sum, which is a ref cell that has a value that is a node. This node inside also has a parent that is a weak pointer, right? And no left-right nodes and the value 1. So this is our first node, and the value 0 is back from our root node. Now the parent, the first one that we print, is the left node, right? So this is the first print parent output, and that's 0, which is true. The left node of root is, the left node's parent is root again, so 0. Then we print the parent of root, and that's 2. That's our node 2. That's correct. Here we drop node 2, so it goes away. And here we get our no more parent output. If you remember from the code above, if we cannot upgrade to a reference counted pointer, we will print no more parent, and this is correct. And this is where Python becomes interesting, because you do not have control over the memory management as you do here in Rust, because you call drop in Rust and it actually does what you want. So this is gone, and you can no longer upgrade to get the parent as you did before. If we do this in Python, at the very bottom here, we have the delete node 2 code. Let's jump this into the middle and go back to our Python output. All right, so on the left, we still have our old code that I reran with another representing output. We can see that after we delete the node, and of course we assign none to parent, well, the parent is none. That makes a lot of sense. However, in Python, we don't have real control over memory. The delete statement on the left here is only a suggestion for the garbage collector to tell him, well, we don't care about this anymore. You can give it a higher priority to get rid of it. But this does not mean we really delete it. To prove this point, we can hop over into the code and insert this as a comment. If we do not assign a none here, but we still keep the delete of node 2, this would be the drop of node 2 in Rust, where it immediately got rid of the node 2. And we run this code now. We actually do not get from the last run's parent non-output, we get a node again, because it is not yet cleaned up, because we still have parent pointing to node 2. All this automagic in Python now knows, well, parent is still assigned and to this memory of node 2. So the garbage collector does not remove this, and you will still keep this. This can end up being memory leaks and, of course, have undesired behavior, because you actually called the delete here, but you didn't really delete. This is the advantage of Rust. You can really code to the lowest level of the CPU and memory usage, and you have full control over everything, which is not the case with, for example, Python. Thanks for watching. Coming up next on the From Python to Rust series will be multithreading.